Unit 1, Lesson 1, we want to start off with hopefully seeing that, I don't know, maybe limits are going to be useful. Maybe not in a I go to the grocery store and use them sense, but whatever. So we're going to talk about rates of change and limits. If you want to do everything, you're probably going to want a calculator with you. So you need to be able to calculate an average rate of change, and the goal here is to understand an instantaneous rate of change, or at least kind of what that means. You need to be able to calculate the slope of a secant line, which also means you need to know what a secant line is. And ideally, by the end of this, you'll be able to use numerical limits in context. So average rate of change, you have hopefully already done that. Average rate of change is just going to be, maybe a good way to say this is f of b minus f of a over b minus a. Average rate of change is simply y minus y over x minus x. Change in output divided by change in input. The slope between 2 points is an average rate of change. So a secant line, I think most of you were introduced to this using a circle in geometry, or at least that's the way I was. A secant line simply connects 2 points on a curve. Now let's pretend this curve kind of went up more. This secant line would extend and hit this curve a third time. You don't have to worry about that because it's like the secant line is doing its job over here, connecting 2 points. We could find the slope of that secant line to give it an average rate of change, or to think of it as an average rate of change. So secant line, secant line, secant line. And what I'm doing here is I'm pushing this secant line closer and closer to the top. And maybe another way to think about that is the endpoints, or the places where this secant line intersects the graph, are getting closer and closer together. If we can get it where those 2 points are basically on top of each other, we call that a tangent line. It's a little weird to say that the tangent line Well, what's not weird to say is the tangent line and this red graph share 1 point. What is weird to say is they have the same rate of change, the same slope at that point. And the reason that's weird is we're kind of thinking about, here I could find the slope between these two endpoints, and then the slope between these two endpoints on the secant line, or the two intersection points, whatever. And here, with the tangent line, it's like those 2 points have merged and we're finding the slope at 1 point, which is why we need limits. And that's sort of a weird idea, but hopefully that's a good visual of what a tangent line is. Okay, so how would we find the average rate of change between 2, 4 and 6, 2? Average rate of change is simply change in y over change in x. So best to give ourselves a label, and we'll write 4 minus 2 over 2 minus 6. If we want to have a sketch of that visually, we would just put in those 2 points, 2, 4, and 6, 2. And there you go. So different format, but kind of the same question. We're going to find the average rate of change of 3x squared on the interval 1 to 4. And this is going to be a theme that you'll see me do a lot. When you have something new, change it into something you can deal with. So once we see average rate of change, we know we're going to do y minus y over x minus x. So you could do everything separate, meaning, y equals 3 times 4 squared. Y is equal to 48. You could do that separate. But it's so much cleaner and more organized to start off with this slope structure, y minus y over x minus x, and just put everything inside. So write y minus y, everything's ready to go. And then as you just simplify, you don't have to figure out what else to do. You've done all the thinking all the way at the beginning. So you should always be looking for tricks. And so I noticed we could factor out a 3, and there's a 3 down here. So we get a much easier 15 than if you had done 48 minus 3 is 45, divided by 3 is 15. whatever. So our graphical support, apparently I'm not willing to do ahead of time. So let's see, 3x squared is a parabola. And let's see, 1, 4. And, oh, this is 3x squared parabola. This is a pretty steep parabola. And, okay, so 15 seems like a pretty good, reasonable average rate of change. So now let's find the slope of the secant line of 3x squared on the interval 1 to 4. And again, we're going to provide graphical support. If you're paying close attention, that's exactly what we just did. Finding the average rate of change of 3x squared on 1 to 4 and finding the slope of the secant line of 3x squared on the same interval 1 to 4 is identical. So we can just redo that. I don't think I need to draw the graph a second time. Okay, so average speed. Now we're going to get into a little bit of an application, so maybe you can see in a physics sense how we might get something useful out of doing limits. Okay, so a bird drops a pebble from 2,000 feet. The distance that the pebble has fallen at any time t is given by 16t squared. What is the average speed of the pebble over the first 3 seconds? Now, I think the first thing to note, there's my bird. Let's give it some wings and a head and a beak. He's going fast. When t equals 0, we get a output of 0. And what that means is 0 is the instant the bird let go of the pebble. And at that moment, the pebble is 0 feet below the bird. T equals 1 is the instant 1 second after the bird dropped the pebble or let go of the pebble. And at that moment, the pebble is 16 feet below the bird, or the total distance the pebble has fallen is 16 feet. When t equals 2, 64 gets spit out. So at the 2-second mark, precisely 2 seconds after the bird dropped the pebble, that pebble is 64 feet below the bird. Okay, so hopefully that helps you understand the context of the equation we have. But if we're doing average speed, that's an average rate of change. This is a change in position divided by a change in time. Right? And the first 3 seconds starts at t equals 0, ends at t equals 3. So hopefully you can tell we can do a little bit of simplifying here. 16 times 0 squared is 0. 3 minus 0 is 0. Let's not bother doing 16 times 9. Let's just divide out a 3 and do 16 times 3 is 48 feet per second. Don't forget to always give context if you can. If you can get in the habit of always redefining your answers in terms of the context of the problem, you're going to have a much more straightforward year. So we're going to say 48 feet per second is the average speed of the pebble over the first 3 seconds. So same pebble, and if you're following along and want to do this with me, you may want to write down y equals 16t squared. We're going to keep using this. So same bird, same pebble, still 2,000 feet in the air, so we don't have to worry about it hitting the ground. How are we going to find the average speed of the pebble from t equals 3 to t equals 4? Well, average speed, average rate of change, change in position over change in time. 16 times 4 squared minus 16 times 3 squared over 4 minus 3. And if we're going to simplify, probably the best way to go is to factor out the 16 and just do 16 minus 9 is 7. 7 times 16, 56 doubled is 112. And then let's not worry about writing out a conclusion here that the average speed of the pebble from t equals 3 to t equals 4 is 112 feet per second, because what we're doing is we're going to, well, you'll see what a limit kind of feels like here. We're going to do a whole bunch of very similar calculations, getting closer and closer to an idea. So now let's calculate the average speed of the pebble from t equals 3 to t equals 3.1. Well, before we do that, maybe we think about, so the bird dropped the pebble. Is the pebble going faster at t equals 3 or t equals 4? T equals 4. So Do you suppose the average speed of the pebble from 3 to 3.1 seconds is going to be more, less, or about the same as the average speed of the pebble from t equals 3 to t equals 4? In either case, we know how to calculate average speed of the pebble, change in y. Well, not change in y, change in position divided by change in time. So 16 times 3.1 squared minus 16 times 3 squared over 3.1 minus 3. I would highly recommend writing these things out every time. This is a structure you're going to do a lot. The reason it's here especially is this is really the form for a derivative. We're missing a limit out front, but we're doing a numerical limit. Anyway, so that's clearly a calculator thing. We'll punch that in and get 97 feet per second. So pretty quick, but less than this 112 feet per second. Okay, so now we're going to keep that going. We're going to find the average speed of the pebble from t equals 3 to t equals 3.01 seconds. And you know the structure. Change in position over change in time. So 16 times 3.01 squared minus 16 times 3 squared over 3.01 minus 3. And do you have a guess how it's going to compare to 97.6? So we get 96.16 feet per second. If you can see where we're going, you know what I'm going to ask you next. We're going to find the average speed of the pebble from t equals 3 to t equals 3.001, which is 16 times 3.001 minus 16 times, squared, minus 16 times 3 squared over 3.001 minus 3. And you should be guessing that this is going to be, well, notice we went from 112 feet per second, t equals 3 to t equals 4, 97.6 feet per second, 96.16 feet per second. You should be guessing, well, less than 96? How much less? Oh, 96.016. And what you should be starting to feel is we're doing a numerical limit. And what we're changing is, this input. And that input, hopefully you feel like, is getting closer and closer and closer to t equals 3, which is weirdly over here. So we are finding the slope of a tangent line. What is the average speed of the pebble from t equals 3 to t equals 3.0001? Or what is that? 1/1000th? 3 1/10,000ths of a second. And well, let's write out the structure first. 16 times 3.0001 squared minus 16 times 3 squared over 3.0001 minus 3. And you probably have a pretty good idea about what's going to get spit out here. And if you do, that means, hey, you've actually evaluated a limit. So we're expecting something 96.0 something. And it actually doesn't matter if you knew this was going to be 0.16. That's kind of an artifact of, this 1 times this 16. What more matters is the direction. You knew as this input, first 3.1, 3.01, and so on, got closer to 3, these outputs were getting closer to 96. And that's the idea of a limit. You have this input getting closer and closer to some place, and the outputs are definitely going towards some number. Now, looking at a table of values, I repeated these time intervals where we were choosing 3 to a time just after 3. But if we're really doing a limit, we need a two-sided limit. So we would also compare time intervals 3 to a time just a little bit less than 3. And so you can see what we, I guess, already wrote, that as the time interval gets closer and closer to being, 3 to numbers closer and closer to 3, the average speed of the pebble gets closer to 96. And that's actually true if you go from 3 to 2.9, 3 to 2.99, 3 to 2.999. We see these average speeds are also getting closer to 96. Now that might be exactly 96. It may be 96.0000081. Who the heck knows? But both going in the same direction. Well, I kind of did all that description for you, so we can skip that. And so, the weird question is, okay, so what about the time interval 3 to 3? If you think about that, 3 to 3, no time elapses. Which means if no time elapses, that's like a photograph in the air. The pebble doesn't fall because that's one instant to itself. And so, if we wrote things out, 16 times 3 squared minus 16 times 3 squared over 3 minus 3, well, that doesn't give us anything useful. That's 0 over 0. Okay? But at the same time, what we noticed is, what I noticed, and maybe you'll agree with, the average speed of the pebble from t equals 3 to times closer and closer to 3, that average speed is getting closer and closer to 96 feet per second. And as it turns out, and you'll know this if you took like Physics 1, maybe you don't know, but you can recreate that using formulas. Well, the instantaneous speed of the pebble at precisely t equals 3 seconds is 96 feet per second. Okay, so I kind of already answered this. Is it possible to calculate the average speed of the pebble at exactly 3 seconds? Well, not if we do it in the average rate of change way, because like you saw, we have something minus itself is 0 over 3 minus 3 is 0, and so that's not really an average speed. But if we put a limit out front, that limit statement makes us think, or at least it will, that you're doing this process and looking for a pattern. So if we write the limit statement, we can figure out the instantaneous speed of the pebble at 3 seconds. All right? So just because we want to get into notation, hopefully you realized those calculations were pretty easy because we did the same calculation over and over. We did 16 times whatever my new time is squared, minus 16 times 3 squared over my new time minus 3. Okay? So if we're writing the limit, what we say is the limit as t approaches 3, that's how we read this, the limit as t approaches 3 of 16t squared minus 16 times 3 squared over t minus 3. And what this means is, well, it means the entire process we went into. So our target value input is 3, and we're going to choose some inputs that are larger than 3, 3.1, 3.01, 3.001, 3.001, larger than 3 and getting closer and closer to 3, as well as inputs smaller than 3 and getting closer and closer to 3, 2.9, 2.99, 2.999, and so on down the line. And we'll plug all of those into the t, we'll evaluate them all, and we'll look, hey, are those y values going somewhere? Or in this case, are those average slopes going somewhere? And that's what a limit is.